Ok, bonjour. Thank you for coming. Merci d'être venu. So, last time we discussed what happens when we allow the ions to move, and since they are much lower frequency than the electrons, we said there's a retardation effect where the effective interaction between the electrons can be attractive. So we try to find out the consequences of that. And in the same way that we computed in the ferromagnet Sz Q equals 0, tau Sz minus Q equals 0, 0 in the normal state, and we found that there was an instability. So if we look at the denominator, so we have the chi 0, 1 plus u minus u chi 0 over 2. So we said that when this denominator vanishes, the perturbation theory blows up. And in fact, it's an indication of a phase transition. So we see the phase transition coming from the normal state. So in the same way here, we decided to study pair susceptibility. And it turns out it's this pair susceptibility that will lead to superconductivity. So in that case, we need sort of psi dagger at time tau, so the same time, let's say up, down. And here we need the psi down, psi up. Okay, and so this is a pair, it's called a pair susceptibility. We go from here and we end up there. So it's really like a scattering process like this. Okay, so to find this response function in the normal state, in the presence of this attractive interaction, we see that what we need is a Green's function here that has these off-diagonal, the so-called off-diagonal element. So we need to see how this changes. And we said that, okay, in the normal state, it's sort of an overkill, but we said that it's useful to introduce this Nambu formalism, which will be very, very useful in the case of superconductivity. So we're doing the job already for the broken symmetry state. So today I will come back at this Nambu formalism, discuss equations of motion and the pair instability. So basically we will use exactly this formalism, but with these Nambu spinners. And then we'll go to the broken symmetry state, in other words, the superconducting state, using an effective medium approach. I'll discuss phase coherence, that is crucial for superconductivity. And hopefully I get to we won't solve the Eliasberg equation, but I will tell you what it is, why it's useful, and it will be quite obvious how to obtain these equations. Okay, even though we won't really write them down or try to solve them. So, are there any questions from last time? Okay, so let's go back to the Nambu formalism. So here I wrote it in the case where we are, let's say, in the superconducting state, it will look like this. So if I look at psi of k, it has two components, one creation operator for spin up and destruction operator for spin up and creation operator for spin down. So we have k and minus k because this is a dagger. And then the adjoint is like this. So even in general, if I use a psi 1, psi dagger 1, I mean, these field operators obey precisely the same anti-commutation relation as any kind of fermion. And so I can define a matrix Green's function. Now it has two indices. You see alpha, beta, alpha, beta. It had two indices before. It was spin up, or spin up, spin down when you look at the transverse susceptibility. So, but now these are Nambu indices. I mean, they are related to these spinners, but we can always go back to the original creation annihilation operators. So here in the normal state, we will need the G12 as usual. We won't assume translational invariance to be able to take functional derivatives. But if we are in the state where the external field is zero, then we'll get this equation. I'll come back to this. I think it's a bit too early to discuss this in detail. So, okay, what am I talking about? External field. So the point is that as we did before, to get these results, we will write a generating function, z of phi, which will be trace e to the minus beta k, times the source field. So with the time ordered product of e to the minus psi 1 bar, phi 1 bar, 2 bar, dagger here, psi 2 bar. Okay, so it has the same structure as before, except that before we put this in the 1 bar and 2 bar, etc., we put the spin indices as well, right? Now we put the Nambu indices. And you see that if I want, for example, if I want G 1, 2, so these are Nambu indices now, 1, 2, I can get this from the functional derivative of the minus the functional derivative of the log of z of phi with respect to phi 2, 1, 2 bar, 1 bar, okay? Because 1, 2 is related to destruction creation, and here they are backwards, so I need to put the indices backwards. Okay, now and just one more thing with this Nambu formalism. If I look at the density, okay, the density in terms of the original fermion, the density operator was psi 1 up, dagger, psi 1 up plus psi dagger 2 1, I'm sorry, down, psi down 1. So that's a density, and this density operator, rho 1, came into the interactions. The interaction V of V, the total interaction. As an operator was equal to a rho of 1 bar, the Coulomb interaction V of 1 bar minus 2 bar, and rho of 2 bar. Okay? But now you see, if we want to stick with this this formalism, we have to change that, because the in terms of components, of this this field, we want to write that it is component 1 of the Nambu operator. But if we look at component 2, and we write it as, if we write psi dagger 2, 2, 1, psi 2, 1, you see that the psi dagger 2 is for spin down. And it is, this is what we want, but the problem is that the dagger, the 2 component is a C, not a C dagger. Okay. So we want to put, this will always be inside the time ordered product. So all that we want is to put a minus sign here. Okay. When we write it in terms of the real fermions, this will be psi dagger. With the minus sign, we switch it and we have it in the right order. Okay. I mean, if you want to be very careful, this generates constant terms and so on, and we get rid of. But yeah, so that's it. So now that then, in terms of this, you see that the density operator is in the Nambu notation is psi dagger 1 psi no. Psi dagger 1 times the third Pauli matrices, from Pauli matrix, tau 3, times psi 1 times V, and now I put 1 bar, V of 1 bar minus 2 bar, and then I have the same thing here, but with the index 2. So psi dagger 2 bar, tau 3, the tau 3 is on top, psi 2 bar. Okay, does that cause any problem? Okay, now you see here I went in the component notation. Here I am in the spinner notation. So you have to think of the indices here. So you have to think that you have psi alpha, tau alpha beta. Let me write it explicitly: alpha beta, beta. Right? So it's this whole thing is a scalar in the Nambu notation. So tau 3 is the Pauli matrix 1, 0, 0, minus 1. So is that clear? So we proceed exactly as before, except that now we have to remember that at every vertex for the interaction, there's a tau 3. Basically, that's it. So now, if we want to generate this correlation function I was talking about, I had a correlation function that was psi dagger, and psi. So if I want to generate this from this formalism, what I need to do is to take the functional derivative of G12, 1, 2, with respect to phi 1, 2. But as we did before for the spin, we will consider this as being at the same point, so that we have psi dagger, and here this will be also the same point. So we have 2, 2. So these are space and imaginary time indices. But these are Nambu indices. Is that okay? So we're computing the pair susceptibility. So we do, just as before, we have two main equations to start with, namely we have the equation of motion. In other words, we have that the Nambu Green's function -1 is equal to G0 -1 minus phi minus sigma. And you have to think of these as matrices in these space-time indices, 1, 2, and also in the Nambu indices. And the other one is that we have that delta phi of G -1 is equal to 0. So that leads that to what we want. Delta G delta phi is equal to minus G delta G -1 delta phi times G. And it's from this that we got these equations of motion. So let us write all the components here for this this subject. So we have minus, oh, I have so little space. Minus, okay, let's start a little bit more to the left. That will be equal to minus G1 alpha bar delta phi alpha bar beta bar. Okay, here I forgot the space-time indices. One, 2 bar delta phi alpha bar beta bar 2 bar 3 bar times G beta bar 3 bar 1. And this is delta phi 1, 2, 2, 2. Okay? Because here I don't need to specify. Before I needed to have 2 plus, 2 minus, because you know at equal time it doesn't make any sense a C dagger and a C. You need to know in what order they are. But because we're looking at when we look at these off-diagonal components 1, 2, we are looking at psi or psi dagger. So then inside the time ordered product there's no problem. And here it's a beta bar 2. Okay, and then I have the piece that comes from the self energy. So I have and here I had a minus sign, so this has become plus. And the piece that comes from the self energy is G1 alpha bar 1 2 bar delta sigma 2 bar, 3 bar, and here I have alpha bar, beta bar. And with respect to phi 1, 2, 2, 2. But, you know, as usual, we will use the chain rule. So the phi dependence of sigma is only through G. So this is delta G gamma bar delta bar of 4 bar 5 bar and times delta G G gamma bar delta bar of 4 bar 5 bar with respect to this phi 1 2 of 2 2, and here I have G, and this is not this curly G, this is the full G. I erased it and put it back. Not very brilliant. Okay, this is the metrobiology, and here I have G delta bar 2 of 5 bar 1. Okay, so what I have done is just to rewrite exactly these equations, except I put the Nambu indices explicitly. Okay, so there were off diagonal G's here because I was applying a field here that breaks the time and space and symmetry. But now I go in the, remember I'm in the normal state. So what should I do in the normal state? In the normal state now, this matrix is diagonal in the normal state. Okay. I've worked as if it was off diagonal because I had this external field, but now I put phi equal to 0. That's the procedure we've used from the beginning. Okay. So it means that here alpha bar needs to be 1 and beta bar needs to be 2. So here I have 1, 2. Fortunately, because I can take derivative with respect to phi 1, 2. And now I have to have 2 bar equals 2 and 3 bar equals 2. So this becomes 2, and this becomes G 2 2 of 2 1. Okay. So I recover what I had before, right? These are the two Green's functions. Okay. Now I do the same type of thing here. So this has to be 1. So alpha bar, beta bar, that needs to be 1, but beta bar needs to be 2 because of this. 2. Okay. Now what else? Okay. Delta G1, 2. Okay. If gamma bar and delta bar are equal to 1, 1, for example, then I would generate a correlation function that has psi dagger psi, because I have 1, 1 here, and functionally differentiating with some off-diagonal component here, I would get, for example, phi phi. So in the normal state, that's 0 because it doesn't conserve the number of particles. Okay. So, so it means that near here, okay, delta was, anyway, delta bar was 2 here. No, delta bar is related to this. Sorry. Delta bar, okay. So these two indices need to be the same, and then 2 equals 4 bar and 2 equals 5 bar. So here I have 1, 2, and here I have 1, 2. And here I have, this becomes 2, 2. No, this stays 5 bar, 4 bar, 5 bar, sorry. For now, 4 bar, 5 bar, 4 bar, 5 bar. Okay. So now there are 2 things we need to do. One is to compute this, right? And for this, we will use this R3 term, okay? Actually, let's leave this as gamma bar delta bar for now. It will be clearer to see what happens. Gamma bar delta bar, gamma bar delta bar. Excuse me. So what is this? So this is, this diagram is minus, and then I have the interaction, and I have the Nambu Green's function. Now at the vertex, I have a tau 3 now. Tau 3. 3 I need to put on top, otherwise I will lack some space. So tau 3, tau 3. And I need sigma here, that's what I'm writing, sigma, but I need sigma 1, 2. So I have 1, and then this can be some alpha for this, excuse me, Green's function. And then I have some beta here. So I have beta 2. Okay? Because I'm scattering, if you want, like this, and then I'm just looking at the factor. Okay? So there's a tau 3 at each one of the vertices. Okay, now, and I took 1, 2 because I'm interested at delta sigma 1, 2. That came 1, 2 because of this. Now, when well, first of all, the Nambu matrices are diagonal, okay? So that has to be 1, 1. And this has to be 2, 2. And that becomes 1, 2. Okay, and we are very happy now because it means that when I take this functional derivative of sigma 1, 2 with respect to g, then it's only, the only g I have is g1, 2 here. Okay? So there's a minus sign here, and there's a minus sign from this, right? Because this tau 3 is 1, 1 is 1, and this is minus 1. So I have no net minus sign here. So the final result is simply plus. And And when I take the functional derivative here, I'm just left with the interaction. And I'm left with 4 bar equals 2 bar and 5 bar equals 3 bar. So here I have 2 bar, 3 bar. And then 2 bar, 3 bar. And when I take this, all I'm left with when I take functional derivative of the g here, I'm just left with the interaction. So this is the interaction, and here I have shown that this needs to be 1, 2 because of this argument here. It says G12, G12. Okay, so now this is V of 2 bar, 3 bar. So I'm taking the functional derivative, I'm just left with the dash line. So this is V of 2 bar, 3 bar. And that's our V that will be attractive. Okay, so now one more, this 5 bar has become 3 bar because this was attached to this. So now I make one more approximation. I take this as local. I take the delta of 2 bar, 3 bar, just to simplify the calculations. Otherwise, it's just more complicated for netting. Okay, so to illustrate what happens, and that's the BCS model finally, I take 2 bar equals 3 bar. In the Eliasberg equations that we will discuss, we don't make this assumption. But here in the BCS case, we make the approximation that this is a delta function of 2 bar, 3 bar. So we have 2 bar, 2 bar, 2 bar, and 2 bar. Okay, so we are ready to, oops, this is V of, yes, just V. Now we are ready to compute this on this whole equation. Now we have the space and time translational invariance. We can take Fourier transforms and everything. Okay, there's just one problem. I need to write this in terms of the Green's functions I know, which are these one here on the diagonal. So this is a G11. Spin up, spin up. But now for down, you remember that when I write the G22, it is not the usual Green's function. It's backwards. So I need to put a minus sign and put this as down, down. And to reverse the order of indices here. Two, one. And this is now I can write this as a G like this. Sorry, if I change the indices, that becomes 1, 2, right? 1, 2. Okay, so I need to do the same thing here. So here I have this, I will get a minus sign from this exercise. Minus, and this will be G down, down. G down, down of 1, 2 bar. And I have the minus minus sign here. Yeah, fine. So this is it. This is now I can write this as a G up up. Okay. Okay. So now I'm ready to take Fourier transform.
I'm not sure to completely understand why we are changing the indices 1, 2.
Because what we have here in the Nambu formalism is psi psi dagger of, let's say, 1 and psi 2, okay, time ordered product. And this is the Nambu, this is now not the Nambu indices. Okay, in the Nambu indices, we have, minus t tau psi 2 1 psi dagger 2 2. Okay, because you see the Green's function is defined like this. So in terms of the Nambu spinners, this component here 2 2 that corresponds to spin down is equal to this. Okay, but this thing written in terms of the spins and the original field operators is down down, but now we have the 2 2 components, so psi dagger and psi are backwards. Okay, when you go from this line to that line. So now if I want to write this as a Green's function, this is equal to minus G down down of 2 1.
Okay, I see.
Because the time ordered product, I can change the indices. So now I'm back to a real, the Green's functions we are used to. And the minus sign I got rid of now in inverting this, so I can need to put it back.
Good, thanks.
So is it clear for everyone? That's the only subtle step of the thing. The rest is just exactly the same as what we did before. Okay. So this is in a way I'm just going through the formalism again. So now when I take the Fourier transform, there will be a difference, right? I will take Q equals 0, so 0 momentum coming in this, and these are lines in the Nambu notation. Huh? But if I go back to the Green's functions in the normal state, you see that now I have things are going in the same direction, right? I'm going like this, 1 2 1 2. So if I take Fourier transforms of this at Q equals 0, so I have 0 thing coming in, the same way as in the ferromagnet, I was looking at Q equals 0. Not all instabilities are at Q equals 0, by the way, so you need to, in general, check. But here, I know the answer, okay? So it comes in at Q equals 0. But in general, you look at some finite Q. So it means that so that here I will have K and minus K. Okay, before I had K plus Q equals 0, so that's K. But now it's K minus K. Okay, because the total momentum that flows in is 0. Okay, so this here is defined as minus the pair susceptibility as a function of coordinates 1 2. So I take Fourier transform, so that's minus chi p of Q, and Q will be 0. and omega will be 0 also. And then here I have, it will be equal to, minus chi 0 p. And here I have this. So you see the way it's done is you have 1 2 bar, okay, 1 2 bar. So it's coming 2 bar here. And then I have a V, and then I have again this same correlation function. Now the arrows are not in Nambu notation, they are in the real, with the real fermions. So if this is minus chi p, and this is minus chi 0, so I have minus chi 0 again, but I have another minus here. So I get a plus chi 0, which is this chi 0 coming from this. I'm taking Fourier transform. V, so chi 0 p of q times V times chi p. And all of this are functions of q. And q will be equal to 0. Okay? So I'm going to erase this. Is it okay? We're done. Sorry it's taking so much time, but better to do it slowly. So I have plus, plus, minus. So I have that chi of p is equal to chi 0 of p divided by 1 plus v chi 0 of p. So we have the same thing as in the Stoner ferromagnetism, right? What we want now is to look for a 0 of this. So the normal state will be unstable if we have 1 plus v chi p equals 0. So all I need, so that's the instability condition. All I need to do is compute this chi p at q equals 0. So what is this chi p? Chi p is equal to T over M, sum over K, sum over I K M of 1 over I K N minus epsilon K times 1 over, let me put the external frequency explicitly, okay? So I will put it equal to 0 in a minute, but just to be sure, okay? I have K plus Q if you want, and minus K. So here I have plus IQN, and here I have minus epsilon K plus Q, and here I have IKM. You will see then why Q equals 0 is the important epsilon minus IKN minus epsilon of minus K. Okay, because epsilon of minus K, and the frequency also is in this index, so I need a minus here, minus IKN. Now, you are all experts in doing Matsubara sums, huh? So let's do that. So T times sum over IKN, we will be left just with 1 over N, sum over K of 1 over IKN plus IQN minus epsilon K plus Q. And here we have plus 1 over minus IKN minus epsilon minus K. And now I can put on a common denominator. And to recover what's on the top line here, I need to divide by 1 over IQN plus epsilon K plus Q minus, minus epsilon K plus Q. Minus epsilon K. And now I can do the Matsubara sums. I was a little bit, I went ahead of myself. T sum over IKN I have not done at this level, but now I can do it. So this is a Matsubara frequency. That's a Bolzanic frequency. So this combination is always odd Matsubara frequency. So I just have a Fermi function of epsilon K plus Q. Fermi function of epsilon K plus Q. And then here I can put the minus sign here, so that I will be able to do the usual Matsubara sum. And this will be F of minus epsilon of minus K. Minus F of epsilon of minus K. And now I look for a thermodynamic instability. So thermodynamic instability is 0 Matsubara frequency. So I put the Matsubara frequency equal to 0. The minus sign I carry over here. And now, what is my instability condition? It is this. So I will put this back here.
So just
yeah.
a quick thing, you forgot the minus K.
Oh, yeah, minus. Very, thank you.
On your right.
Minus.
And then on your right, yeah, here. All right.
Thank you. And I have minus 0 also. F of minus epsilon of minus K. So, but F of minus epsilon is 1 minus F of epsilon. So it's 1 minus F of epsilon of minus K. Okay, so let me write this instability condition. As you see, there's a number of minus signs. So if I get the correct answers, it's because either I did it correctly or I did an even number of errors. Okay, so you have to check and tell me what's the verdict. So then I write this like this. So the instability condition is 1 equals minus V times this susceptibility. So this susceptibility is, let me transform this into integral. We'll figure out the signs in one moment. D cubed K over 2 pi cube. And now for the signs. So if I combine these two signs here together, I have, I think I did only one sign mistake, so that's a problem. Okay, epsilon of minus K, I will assume that the system has a parity or time reversal symmetry, which means that epsilon of minus K is equal to epsilon of K. Okay. And you see why Q equals 0 is nice here. It's because Q equals 0 will mean that these two things are together. So when we get to the Fermi surface, this should have been zeta, I'm sorry. So we measure with respect to the Fermi surface. So when this goes to 0 at the Fermi surface, they will go to 0 at the same place. So it's Q equals 0 that will be larger. So here we have minus, minus. So this is 1 minus 1 minus 2 f of epsilon K. And this is plus here. No, this was still f of epsilon of minus K, I'm sorry. Divided by 2 epsilon K. Okay, these two add up now. Okay, very good. So you see that when this whole thing is equal to 1, then I can have an instability. And if V is at this quantity, 1 minus 2f of epsilon K is equal to that, you can check. This is 1 minus 2f of epsilon K is an hyperbolic tangent. So when the hyperbolic tangent changes sign, this changes sign also. So this side is positive. Okay. If V is repulsive, V is positive, then there will never be a solution because I have a positive number equals a negative number. Okay. But with an attractive V, I can have a solution. We will discuss what happens when V is not a delta function, but depends on direction. This will change what we have done. Okay.
And so, quick question here: if V is negative, then is there always an instability?
Yes, that's a good question, and the answer is yes.
Right.
So that's what is very nice about this, because you see. Thank you for this question. This I can write as 1 equals minus V times the integral d epsilon times the density of states times the hyperbolic tangent of beta epsilon K over 2 divided by epsilon. And there's no K anymore because I went to the density of states. So you see what will happen is that take a constant density of states just for discussion. Then I will get minus V times the density of states at the Fermi level times this integral d epsilon hyperbolic tangent of beta epsilon over 2. I hope I have time to solve this equation for true. And I forgot the 2 here. And you see the hyperbolic tangent is equal to 1 when the argument is large. When the argument is small, then it simplifies the epsilon. So basically, I have to do the integral up to some cutoff of d epsilon over epsilon 1 from something that's of order the temperature, because when epsilon is less than the temperature, beta epsilon is less than 1, then that becomes beta epsilon. That simplifies, there's no more 1 over epsilon. So, but I will get a 1 over epsilon to integrate over an interval that's of order temperature up to lambda. And what is this? That's the log. That integral is equal to the log of lambda over temperature. So that's called the Cooper logarithm. Okay, so that's a logarithm we find in the Cooper channel. And then you see that it always has a solution, because if t goes to 0, the log becomes log of infinity, so it becomes arbitrarily large, right? And so if v is negative, the log has as a consequence that there's always a solution. So for attractive v, we are in business. We have yeah. So the reason there's a logarithm is that it is as if, you know, on the Fermi surface, we always look at electrons and holes that are, or particle actually, so it's particle that are time reverse pair. Okay, there's k and minus k, and so everywhere this scattering can occur. So Cooper came to this equation not by using this complicated formalism. The complicated formalism, we will, as I see, it will be useful once we go in the superconducting state. But I mean, he did the equivalent of this. So he looked at the cross section for two particles that are scattering, using the Pauli principle. In other words, you don't allow particles that, you know, the two particles are hindered by the presence of the Fermi C, then you have problem. This is better than the Cooper problem, actually, because that includes the whole contribution. In the case of Cooper, he was just looking at the particle contribution. So this gives the BCS equation for the transition temperature. You see, there will be this log, as I said, and so we can, but it's late now, so we'll do this. Next time. Actually, I won't solve this next time. We just know that there's a solution, and I'll go directly to the superconducting state. So I did half of what I was supposed to do, but I hope I did it correctly. So any question? Okay, so I'll stop the recording. If you have some private questions, you can stick around and